In this video, we're going to work a couple of problems for you. The first problem we're going to look at is a problem just to find the confidence interval for a population mean. So we have a problem that is relatively simple just to begin with, and I'm going to create a fresh page for that. Alright, so we have the following information. We're told that we have the mean monthly rent at assisted living facilities is the following, $3,486. So mean monthly rent at assisted living facilities. Mean So it turns out that we have a value of $3,486, and that is based on a sample of 120 facilities. So that means that this value here is our sample mean. The number of facilities, 120, and assume that the population standard deviation is $650. So the first question is A, find a 90% confidence interval for the true mean monthly rent. For the true mean monthly rent. Now when you see things like true mean, that's the same as saying population mean. Okay, so we know sigma. In this case, sigma is known. So if sigma is known, then we will estimate the population mean using Z alpha over 2 sigma over the square root of n. Do we have x bar? Yes, we do. We have n. We have sigma. Now we need the z value. Now we're told a 90% confidence interval, and there was a little table that I gave you before that said for 90% confidence interval, z alpha over 2 is 1.645. For a 95% confidence interval, z alpha over 2 is 1.96, and for 98% confidence interval, z alpha over 2 will be 2.33, and for 99% confidence interval, z alpha over 2 will be 2.575. Okay, so you need to just make a note of that somewhere and basically use it when you need to. Memorize it and use it. In case you're wondering how I got those values, I explained that a bit earlier in the video on that introduced interval estimation for population mean. So, and then also the textbook does explain how those values come about. So I'm just going to just use it here in this case. So we would have 3,486 plus or minus, in this case 90, we're looking at 90% confidence interval, 1.645, and then sigma is 650 over the square root of 120. So that's our margin of error, and that's our point estimate. I want you to keep that in mind. Once we figure this out and do all of the mathematics behind it, we will get 3,486 plus or minus $97.61. Right? So that 97.61 is our margin of error, which then gives us that following interval that the mean is between 3388.39 and 3583.61. 3583.61. I'm assuming that you know that how to just add and subtract the 97.61. So 3486 plus 97.61 will give us 3583.61. And when we take away 97.61 from 3486, we will get the lower limit of the confidence interval. So to get the lower limit of the confidence interval, you do the subtraction. To get the upper limit of the confidence interval, you do the addition. And that gives us the answer we're looking for. Now, what if we wanted to find a sample size that would give us a margin of error of $50 instead of the 97? We see 97 is a bit large. Can we narrow that down to be within $50 of the actual mean? So in that case, we would need to see the following. So now our margin of error would be equal to $50. And so 50 is equal to Z alpha over 2 sigma over the square root of n. We don't know what n is, but we know what sigma is and what the z is. We still want the same 90% confidence interval for a 90% confidence interval. So what is n? The sample size. So when we compute that, n is equal to z times sigma over the margin of error squared. You may recall that formula. Z is 1.645, sigma was 650, and the margin of error we said is 50. So if we compute that, we will get handy dandy little calculator. 1.645 times 650 divided by 50, and when we square that, we have 457.3, and we always round up to 458, so approximately. So to get an estimate within $50 of the population mean, we need 458 facilities. Now in the first instance, we surveyed 120. Now we're looking for 450. That's going to cost us some money. So sometimes you have to balance the amount of precision that you want with the sample size that you have. All right. So that's a fairly straightforward question involving interval estimation of the population mean with sigma known. Now let's look at a case where sigma is unknown. All right. So in the case where sigma is unknown, I have an example here for you. So we have this one. A survey is conducted by the American Automobile Association. Showed that a family of 4 spends an average of $215.60 per day while on vacation. Suppose a sample of 64 families of 4 vacationing at Niagara Falls resulted in a sample mean of 252.45 per day and a sample standard deviation of 74.50. Develop a 95% confidence interval for the mean amount spent per day by a family of 4 visiting Niagara Falls. All right. So we do want a confidence interval estimate of the mean. We know that part. And we have 2 choices. We could have either x bar plus or minus z sigma over the square root of n, or x bar plus or minus t alpha over 2 degrees of freedom s over the square root of n. Which of those 2 should be used? Well, we would only use this one if we knew the population standard deviation. Let's see if we are given a population standard deviation. We're not from this question, but we're given the sample standard deviation. So which means that we have to use the t-distribution for this question. All right? So let's put our values down. What do we know? We know that it is believed that the true value is $215.60 per day. That's what is believed. However, our sample gave us some different information. The number of families in our sample was 64. So here's what we have. Sample size is 64. We obtain a sample mean of 252.45. And a sample standard deviation of $74.50. A 95% confidence interval is what we're looking for mu. Now, given that we've already said that sigma is unknown, we know we're going to have to use x bar plus or minus T alpha over 2 S over the square root of n. Let's find what T alpha over 2 is. Degrees of freedom. Well, we know that 1 minus alpha is the confidence level, which we are interested in 95%. Therefore, alpha is 0.05. Alpha over 2, 0.025. The degrees of freedom is the sample size minus 1, which is 64 minus 1, or 63. So essentially, we are looking for a t-value with the area in the tail as 0.025 and 63 degrees of freedom. Let's see if we can find that. So I'm going to insert, I'm going to insert my t-table right here so that we can look at it together. The tables, we need t-table. And here we go. So remember, the area in the tail is 0.025, the degrees of freedom is 63. So on this page, the maximum degrees of freedom that we have is 34. Let's go to the next page and see if we can get 63. Here's 63 right here. So we have 63, and the area in the tail is 0.025. So if we come down this column and we look at 63, we'll have 1.998. All right? So that t-value is 1.998. So our confidence interval would be 252.45 plus or minus 1.998. S is 74.50 over the square root of 64, which gives us a margin of error of 18.61. So 252.45, 252 plus a margin of error of 18.61. So the mean lies between 233.84 and 271.06. All right, so that's the answer to that part A of that question. Now, I believe there's a part B to that question. Let's see what it says. Based on the confidence interval from part A, does it appear that the population mean amount spent per day by families visiting Niagara Falls differ from the mean reported by the American Automobile Association? Now, remember what the American Automobile Association actually reported. They reported it was 215.60. 215.60. So that's what they're claiming. Automobile Association reported 215.60. Let's see where this number falls in that interval. Does it fall in the interval? The answer is no. So if we were to actually draw this on a scale, the 215 is somewhere down here. All right? So as you can see, if the mean is somewhere in that interval, the 215 is outside of that range. And so therefore, it doesn't really gel with what they suggested that it is. All right? So therefore, it would seem that there's been an increase in the average amount of money spent by a family of four at Niagara Falls. That number is now different. So yes, it differs. As any value in that interval is greater than 215. So there is evidence actually that the mean has actually gotten bigger. People are spending more, which makes sense. Over time, it's becoming more expensive. Food is getting more expensive. Fuel is more expensive, etc., etc., etc. All right. So that's that question. We did both a large, when I say large sample, a problem involving the normal distribution, so using Z. We did one involving T. We found sample size. Let's find sample size in this case. Now, currently, our margin of error is 18.61, which is $18.61. What if we wanted an estimate within $15 of the mean? What sample size do we need? So if we're looking to now have, we want a margin of error of $15. What sample size is needed? So the margin of error, remember that even though we start off with using the t distribution, we cannot use the t in finding the sample size. So therefore, we will say that this is equal to z s over the square root of n, in which case n is z s over me squared. So our z value now, when we're talking about 95% confidence interval, is 1.96. So it's not a whole lot different from the 1.998 that we use. So it'll be 1.96 times 7450 as our standard deviation over the margin of error of 15. And if we square that all together, we should get the following answer. 196 times 7450 divided by 15, and then if we square it, we have approximately 95 families. So this is 95. So if you wanted to estimate the true amount of money spent per day to within $15 of the actual mean, we would need 95 families to participate in our study. All right? So that answers that particular question for us. So now let's do one more involving proportion. Let's take a question here. Question number 54. Okay. So we're told that we have, let's make sure you could see that. The USA Today's CNN Gallup survey of 369 working parents found 200 who said they spend too little time with their children because of work commitments. What is the point estimate of the proportion of the population of working parents who feel that they've spent too little time with their children because of work commitments? So when we say point estimate, we mean the sample value. So because we deal with proportion, we know that proportion is given by P bar, sample proportion, is the number of observations over the sample size. Well, we had 200 over 369, not a very nice number. And when we compute that, we have 0.5420 approximately. All right? So that is our sample, our point estimate. Our sample estimate or point estimate. Now, if we want to find a 95% confidence level or interval, what's the margin of error? Well, we know margin of error is simply Z for that confidence limit into this times the square root of P bar, 1 minus P bar over N. So that should be for a 95% confidence level. Z is 1.96. And again, you could go and verify that. 0.542 times 0.458 over 369. And that turns out to be 0.0508. And all we now have to do to find the confidence interval is to take now P bar plus or minus the margin of error, which gives us 0.542 plus or minus 0.0508, and so therefore P is between 0.5928 and 0.4912, or 49.12% and 59.28%. So that's the answer we're looking for. All right, so notice that the margin of error was 5.08%. What if we want a margin of error of, say, 2%? What should our sample size be? So margin of error of 2%. So I'm going to add a D section to this. Of error of 2%. What sample size is needed? Let's put for a margin of error. So in that case, your margin of error, we remember, is given by Z times the square root of P bar 1 minus P bar over N. When we manipulate this formula, it turns out that N is equal to Z squared P bar 1 minus P bar over ME squared. So we want a margin of error of 2%. And so that would be 1.96 squared times 0.542 times 0.458 over 0.02 squared. That should give us our sample size. So it's not very difficult if we simply just follow the formulas for that. And so we have 1.96 squared times 0.542 times 0.458 equal, divided by 0.02 squared. Who gives me 2384. That's huge. So to get down to a 2% level of precision, I need, when I compute that, 2,384. Parents to participate in this study. So to go from a 5% margin of error, sorry, not 5%, yeah, 5.02% margin of error, down to a 2% margin of error, you have to increase that sample size significantly. And you have to ask yourself, is it worth it to go and spend all that money to survey an additional, we have 369, so 2384 minus 369, 69 from 84 gives us 15, so that is 2315, sorry, 2015. So 2015 parents, additional parents, is what we need to get this level of precision. I don't think it's worth it. With a 5% margin of error, I think that's a fairly decent estimate of the population proportion. All right. So, folks, that brings to the end 3 quick videos. One that looked at the introduction to interval estimation of the population mean, with sigma known, sigma unknown. Secondly, the interval estimation of population proportion. In both cases, we looked at, for a given margin of error, what sample size is needed. And then finally, we have in the final video some work problems, 3 example problems. And then if you could work through the rest of the problems that I post for you, then that would be fine. Okay? Good.